we've seen a lot of, but we haven't named them as such. So I want to be clear about what you need to be able to do on this stuff. The goals here are identify what we call redox reactions, which are chemical reactions that involve a change in oxidation or involve oxidation and reduction. And I'll show you what that means in a little bit. And then identify which chemicals are oxidized or reduced. So that's what you need to be able to do from this stuff once we go through it. Let's first talk about those definitions. What does oxidation or reduction mean? Does anybody know or remember?
Oxidation is burn.
Yeah, well, yeah, it's related to that. Oxidation sometimes is discussed as burning, because burning is usually oxidation. What else have you heard that term used for?
Gaining an electron.
Close, it's losing electrons, but yeah.
I remember that.
Yeah. Has anybody ever heard of like metal? Like if a metal is shiny and then it kind of gets dull, we'll say it gets oxidized or something like that. And that all fits in this category of oxidation. That's all good examples of oxidation. You can also probably guess from the word itself that it has something to do with oxygen. And in all those cases that we've talked about, burning as well as like tarnishing or that kind of like dull appearance that happens on metal, rusting also, those are all examples of reaction with oxygen. And that's a big category, that's a big part of oxidation, but we're going to define it even more generally than that. We're going to say oxidation is a loss of electrons. So that means something changes its charge in such a way that it loses electrons. So if it's losing electrons, is it going to become more positive or more negative? More positive, right. So in a course of a reaction, if you have, let's say, something that goes from Fe2 plus to Fe3 plus, that's more positive, right? So that's an example of oxidation. It's become more positive. That's a somewhat unusual example. Normally what we see in these types of reactions is going from 0 to a plus or going from negative to 0. So for instance, something like aluminum on one side becoming aluminum ion on the other side. What's the charge of the aluminum on the left? It's 0. Any element by itself, its charge is 0. So this has gone from 0 to +3. And that's an example of losing electrons. Each atom had to lose 3 electrons to do that. Another example of oxidation is if something like oxygen goes from oxide to oxygen, which we know is a diatomic element, so it would have to be an O2. But let's say you have something like aluminum oxide or sodium oxide or whatever oxide, and you do some reaction, and then the other side of the reaction is O2. That's an example of something going from -2 to 0. That's also a loss of electrons. If it started at -2, lost 2 electrons, it would be 0. So those are all examples of loss of electrons. You can either become more positive, you can go from 0 to positive, or you can go from negative to 0 or just to less negative. Usually it's to 0. But electrons don't just disappear. They don't simply go away. So that means that something else in the reaction has to get those electrons that are lost by whatever is being oxidized. And the thing that gets the electrons, we say, is reduced. So the counterpart to that is reduction. So that could be something like the opposite, where O2 oxygen becomes oxide. Right. That could be something like sodium plus becoming sodium metal. Unlikely, but that happens. Unlikely with sodium anyway. So something becoming more negative. Let's write that. So up here it became more positive. Down here we're going to say this becomes more negative. All right. So that's how we call these things redox reactions. If we go back up here. Oh, there it goes. Redox reactions. Read whatever RED for reduction and then OX for oxidation, because these things always go together. You never have just oxidation or just reduction. You always have both things happening at the same time. So the trick, or not the trick, but the idea then is to recognize what's happening, what's changing charge. So let's use an example from our quiz and see how we can see this as a redox reaction. One of the reactions was iron 3 oxide plus aluminum gives aluminum oxide plus iron. So I'm just going to tell you this is a redox reaction and not balance. Balance it. Sorry. How can we tell that something's changing charge in this reaction? So if you're looking at this reaction, you don't know if it's a redox reaction or not. How could you figure that out? How could you determine that?
Is it because the iron's by itself now?
Yeah, that's one big clue in these reactions, is look for elements that are by themselves. Both the aluminum and the iron. And pretty much any reaction that you see a neutral element is going to be a redox reaction. It's going to fall into this category. Because if something's a neutral element and then it becomes a compound on the other side, that pretty much tells you it has to do something. It has to do something with its electrons so that it can make a compound. So if you see a neutral element on one side and then that same element in a compound on the other side, that's going to be a redox reaction. Now we can look into it a little bit further and prove that. We can say aluminum right here, the charge is 0 because it's by itself. What's the charge of aluminum in aluminum oxide? Close. Still close. Less close. Anybody? Positive 3. Yeah, that's plus 3 in aluminum oxide, because oxide is -2 and there's 3 of those. So aluminum has to be plus 3. I mean, there's only so many numbers, so you would have gotten there eventually, right? Yeah, so plus 3. So if it's going from 0 to plus 3, it's becoming what? More positive or more negative? Yeah, so aluminum goes from 0 to plus 3. So is that an example of oxidation or reduction?
How is it 0 if there's 2 in front of it?
The charge on it is 0.
Okay.
Yeah.
Oh, oxidation.
Oxidation, yeah. So it's starting with a charge of 0, ends with a charge of plus 3. That's oxidation. And so what do you think is then being reduced? Iron, right. Iron is starting from plus 3 and going to 0.
I have a question.
Yes.
Why is the charge of aluminum on the left side 0? Like why, how do you know that it's 0?
Any element by itself has a charge of 0. So whether it's like literally just by itself, like aluminum there, or if it's something like O2 or H2, that's still only one kind of atom in that, so it's still 0. You only have the charge when you have compounds with different elements. So we can look at a reaction like this and see which things are oxidized and which things are reduced based on what the changes in charges are. And when I was looking through the homework in this one, this rule about looking for neutral elements covers like 90-some% of everything. So of everything that you'll see. So that's really the main thing you want to look for whether or not something is a redox reaction for us. If we look more broadly at all the different things that could happen in chemistry, that's not a great rule. But for these types of reactions that we're dealing with, that works pretty well. Okay, so let me show you what how we would ask a question like this in something like the book. Does anyone else have a question? Oops. Oh, sorry. Okay. All right, so we've got some different reactions. And in each case, we want to identify what is oxidized and what is reduced. So see if you can take a look at those reactions and think about what is losing electrons and what is gaining electrons. That is, what's becoming more positive, what's becoming less positive, more negative. And see if you can decide which of the two reactants is oxidized and which one is reduced in those 4 reactions.
I don't know. Joe, I have seriously no idea. Mm-hmm. It has it too. Okay. It's the most.
What number? It's the most charged out of all of them, really not, so that's not enough. Oh, well, then it's 7. No. Yeah. It's hard to determine which one's which when they're all named the same thing. Okay. Right, then I don't know. It's on the mountain. 6.
Group 1. Right.
Oh, yeah. So minus 1 is when she started out. Oh, no, 6. Okay.
The allies are positive ones, so reduction. And then that would be negative one.
Okay, let's take a look at these. So what you want to do for these types of reactions is map out the charges. Figure out what is the charge on each thing on each side of the equation, and then look for the ones that change. So what's the charge on lithium on the left side of the equation? It's 0 because it's just lithium. Okay? Don't worry about the subscripts or the coefficients. If there's nothing else with it, if it's not in a part of a compound with other stuff, it's just an element and its charge is 0. So lithium goes from 0 to what on the other side? Positive 1, right. And how do you know that? Yeah. So I think some people are getting confused that this is like a new thing. It's not really a new thing. When we're looking at the ionic compounds, everything has the same charge that it did in chapter 6 or whenever we did this before. So if lithium is in a compound with fluoride, the lithium is +1 and the fluoride is what? Got to be -1, right? And you can either figure that out from knowing that lithium is +1 and they have to be 0 overall, or you can know that fluorine usually makes a -1 ion from its position on the periodic table. So that means that fluorine in this reaction is going to go from 0 to -1. Okay. So which is an example of oxidation and which is reduction? And this is easy to flip, just like the exothermic and endothermic thing.
Fluorine's being oxidized and lithium's being reduced.
Close. Yeah.
Oh, yeah.
So there's various ways you can remember this, or you can try to remember this. Anybody have a good one? Anybody know? Remember any of the good? Like, how do you keep straight which one is oxidation and which one is reduction?
Leo Gur.
Leo Gur. Okay, that's a good one because it's like a lion. So Leo is
Yeah,
loss of electrons is oxidation.
Yeah,
What's the
just like
Gur?
Leo the lion goes Gur.
Okay.
Or you could think about oxidizing as also burning, and you burn, you lose things.
Oxidizing is burning, and when you burn, you lose things. Yeah, that works. Somehow, remember, oxidation means losing electrons, whether it's lions or whatever. I'm sure if you look up, that there's a bunch of ones that people have come up with, and you can probably find one that sticks in your brain. Yeah.
I feel like it's easy just to think that it's like opposite, because reduction I would think would be lose, but if I just remember that it's opposite.
It's opposite of what you think?
Reduction is positive.
Okay, that's good. That works for you. That may be confusing for other people, but who are not confused in the first place. But that works. That's yeah. Like I'm always wrong, so I just need to flip my answer, and then I'm good. Yeah. Yeah. So in this case, lithium is oxidized, and fluorine is reduced. Another way you can think about it, although this doesn't work for the rest of the reactions on this page, whenever you have a metal and a nonmetal, the metal is usually oxidized and the nonmetal is usually reduced. But the rest of these have either two nonmetals or two metals, so that doesn't really help. Okay, so let's look at the next one. What's changing charge in the reaction in B? The chlorine and the iodine, yeah. And what's staying the same? The potassium. Potassium doesn't change charge in this one. It's plus on the left and plus one on the left, plus one on the right. So chlorine goes from 0, because it's all by itself, to -1. And iodine goes from -1 to 0. Whoops. Sorry. So 0 to -1, -1 to 0. Which of those represents reduction, which is oxidation? So what represents a loss of electrons? Going from 0 to -1 or -1 to 0?
-1 to 0.
-1 to 0, because that's getting more positive. Getting toward the positive. Imagine like a number line in your head or something, you're getting more positive. So iodine is oxidized. Let's keep track of this. So this is oxidized. This is reduced.
Would it be the opposite though for the top one? Isn't the oxidized losing? So then the
Yeah,
one should be.
So losing.
but losing makes it more positive because you're losing a negative electron.
Oh, okay.
So when you go from 0 to +1, you've lost an electron.
Oh, I got you. Yeah.
All right, third one. This one, we've just got a reaction of two metals, aluminum and tin, and their charges are shown, so they're actually not shown in compounds in this particular reaction. So this one makes it easy, at least, to figure out the charges, because aluminum goes from 0 to +3, as it says right there, +3, and tin goes from +2 to, I don't know why I wrote that again, but +2 to 0. So which of those is a loss of electrons? Aluminum, right? Getting more positive. Have to lose electrons to get more positive. And then tin is doing the opposite. Notice here also, you can't ever have two of the same. If something's losing its electrons, something else has to be gaining it. So all you really need to know is one, and then you can figure out what the other one is. If you can be sure about one of them, you know the other one is the opposite. All right, and then the last one What is changing charge here?
Iron and
Yeah, iron and copper. So what's staying the same?
The salt.
The sulfate, or the sulfur and oxygen, yeah. All right. Iron's going from 0 to what? +2. And that one we can't remember, we can't figure out from the periodic table. We figure that out by knowing that sulfate is -2, and a compound between sulfate and iron has to be +2 to balance that out. And then copper is going to go from +2 to 0, same kind of thing. So which of those is oxidation and which is reduction? Yeah, first one's oxidation, and that means this one must be reduction. So that's oxidation and reduction. The book has some nice practice there. Okay. Let's start talking about gases a little bit, and then we'll take a break. This is now chapter 8. Now this chapter, we're not really doing the whole chapter. We're doing the concepts of the chapter. We're not doing the calculations of the chapter. And the book does it differently. So when you look like, well, let me just show you, and then you'll see what we do differently. It makes it hard to do homework kind of in this chapter, because if you look at some section, it's all about solving these various types of equations for what happens with gases, and we're not doing that. We're going to skip all those equations. So this is just going to be a very kind of concept-oriented chapter of like what happens when you do this, what happens when you do that, that kind of a thing. So when you're doing your homework, make sure you follow the listed suggested problems on Blackboard, because otherwise you could get really bogged down in stuff that we're not actually doing in this class. All right. Anybody know anything about gas? Anybody have any gas right now? Maybe a little? No.
It's combustion, right?
It's what?
Combustion.
Combustion often creates gases, yeah. But we're going to talk even more generally than that, just gases as a state of matter. Does anybody remember when we talked about the states of matter? What is the defining thing of gas? Like what is it that makes a gas different from a solid or a liquid?
There's little to no attraction between the molecules.
Yep, there's little to no attraction between the molecules. So what does that mean for like how a gas behaves, like let's say in a flask or something?
Particles move very fast.
Particles move very fast
And then far apart.
and they're far apart. And that means that they can fill a container, right? So a gas has no fixed volume and no fixed shape. It always, remember, a liquid takes the shape of its container but keeps its volume. A gas takes the shape and the volume of its container. So gases, am I like zoomed out or something? I am zoomed out. Gases take the shape and volume of their containers, which means if I have a 250 milliliter beaker, there's 250 milliliters of gas. And it doesn't matter how much gas I put in there if I pressurize it up. There's more gas in there if I pressurize it, but it's still 250 milliliters. So we don't change the volume. The volume is fixed by the container. Now, a lot of the stuff we're going to talk about today makes a lot more sense when you actually see it in action, and we're going to do that on Wednesday in lab. I couldn't bring it all down here because a lot of the stuff is not safe really out of the lab, but we will see that on Wednesday and hopefully, so try to kind of keep in the back of your head the stuff we talk about today so that it makes more sense when we actually do it on Wednesday. All right. Measuring gases is a little bit trickier than liquids or solids because you can't weigh it, right? You can't just like, I mean, you can if it's heavier than air, but you can't just pour some gas in your weigh boat and then dump it in your reaction or whatever. The volume thing we just talked about, we can't measure it by volume the way we do liquids because it just fills the container. So how do you measure gas?
Some pressure thing.
Yeah, some pressure thing. Exactly, it's pressure. Yeah. Does anybody, like if you see a gas tank, it has those like those dials on it, and those dials are measuring pressure. So that's how we usually measure gas. How much pressure is it under? So let's talk a little bit about what that means. The official definition of pressure is force per unit area. That basically means how much, not just how much are you pushing down, but how much are you pushing down over a particular area. So like if I'm walking through like a muddy field after it rains or something, I have the same force that I'm exerting on the ground because the force is my weight. But if I'm wearing like really pointy heels, as I do when I go through muddy meadows a lot of the time, what's going to happen? You sink in, right? And if you're wearing snowshoes,
The worst.
you don't. Yeah. So that's a difference in pressure because the force stays the same. The force is your weight, but the pressure changes with the area that it's distributed over. So anybody know some units of pressure? PSI is one. That stands for pounds per square inch. And that means we can also write it kind of like our fractional units, like we talked about grams per milliliter or something. So we could write pounds per 1 square inch, which is actually an inch squared. So how many pounds per inch squared? What do we use that unit for? Anybody used it for anything? Yeah?
An autoclave at work.
An autoclave at work? Okay, yeah, so you're pressurizing the steam in the autoclave. We'll talk about why that is. Yeah, so we say tires. Yeah, you're checking tire. What's like an average tire pressure?
38.
Yeah, somewhere in the mid-30s, right? Depending on your car. Public service announcement, check your tire pressure. It's important. Although nowadays, I guess fancy cars have those things that like check it for you, and it like tells you if it's low. Yeah. What? Well, then you should probably fix your tires. No, you think it's
My
good?
car will tell me even if the spare in the back, if the pressure is low there.
Oh, really?
It's constant.
Wow. It's these fancy cars of the future. But anyway, yeah, you can cause some problems if you don't have the appropriate pressure in your car tires. So make sure you check that. Maybe check it when you go home today or something. Anyway, we don't use PSI that much in lab because it deals in the English system or the imperial units. Pounds and inches don't play nice with centimeters and meters and things like that. So anybody know what we would use in the lab? What our normal pressure units will be? There's a couple different ones. The main ones we're going to deal with in this class, the ATM, which stands for atmosphere. One ATM is the atmospheric pressure at sea level. So the pressure that the atmosphere exerts on the Earth at sea level. And then the other one is kind of a weird unit, millimeters of mercury. What? See, it is weird. Yeah. Somebody said something. It's kind of a weird unit because it's a pressure unit, but it's in millimeters, which is not a pressure unit. So what's happening there? You know where that comes from?
Is it like the thermometer, like a temperature thing?
It's kind of like that, yeah. It has to do with the unit that measures it. So if we look at, where's the picture here? There. This is a measurement tool called a barometer, which measures pressure. So if you put a bunch of liquid mercury in a dish, don't do that, by the way, it's poisonous. But before people knew that, they put a bunch of mercury in a dish. And the real danger with mercury is actually it has what we call a high vapor pressure, which means if you just have a bunch of mercury sitting there, it just looks like this cool silvery stuff that's like floating around on the table or wherever, but it's actually giving off invisible vapor. And so if you're doing stuff with mercury, you're breathing in the vapor. And that's why everybody kind of freaks out when mercury breaks and you have to go like vacuum it out with special stuff, because those particles from the mercury actually end up in the air and you end up inhaling them. So anyway, so don't do that. But a long time ago, we measured pressure by making a dish of mercury, taking a tube that had no air in it, so a completely evacuated tube, and putting it upside down in the mercury. And what happens if you put an evacuated tube upside down in liquid? Yeah, it kind of sucks back up into the tube. And it's not really sucking, it's more getting pushed. It's the atmosphere is pushing down on that dish of mercury and pushing it up into the tube. And so that's how you would measure atmospheric pressure, is how much is the atmosphere pushing on the mercury and how far up the tube is the mercury traveling. And the distance for 1 atmosphere turns out to be 760 millimeters of mercury. So you should know that 1 atmosphere, which is the atmospheric pressure at sea level, is 760 millimeters of mercury. This unit is also sometimes known as torr, depending on the devices you use. It's not exactly the same thing, but it's more or less the same thing. So we'll use them interchangeably. So in that way, we can convert from millimeters of mercury to atmospheres, back and forth like that. But those are the units we're going to mostly use. There's another pressure unit in the metric system called the Pascal. We probably won't use that one as much, but we might as well list it here. Let's say, okay, here are the important ones: the atmosphere per millimeter of mercury. There's also PA, Pascal. And there are, I'm going to get this wrong, 101. Oh, I don't have it here. I don't remember the exact, there it is, 101. Oh, I was right. Okay, 101 pascals is 1 atmosphere.
Do you know those?
No. Oh, no, I'm sorry, 101 kilopascals. So 101,000 pascals is an atmosphere. No, I'll give you these numbers if you need them. But these are some different ways that pressure is measured, and that's how we measure a quantity of gas. So if you look at something like a gas cylinder, you know what a gas cylinder is? The like big tank thing. That tank keeps its same volume. The tank doesn't get bigger and smaller. But as the gas goes out of it, as you use it for whatever you're using your gas for, the pressure goes down. And so you measure the pressure to kind of determine how much gas is in that tank. And when the pressure goes down close to 0, then you know you've used all the gas from the tank. All right, let's stop there. I don't know, how much time break do you guys want? You're all just like, I just want to go home. I don't want to. Just keep going?
Yeah.
All right.
Yeah, that sounds good.
Okay. No.
No?
It's all recorded. You can just leave for a little bit and come back if you want, if you need a break. We don't have that much to talk about tonight. Should be okay. All right, we'll just do our break at the end. Okay, so the main part of this chapter is that we're going to look at 4 different relationships and talk about why these things happen with gases. And it's really important to know about these different relationships. So that's what we're going to.
Hold on a second.
That's what we're gonna do. This is the main part of this chapter, and a lot of this you already know just from like life experience, but we want to put it into the particular terms of what we're doing. First relationship we're going to look at is pressure and volume. So what happens to one when you change the other? What? Not quite. Not quite. Yeah, not close though. So if you decrease the pressure of a system, what happens to the volume?
Decrease the pressure of a what?
Of something. So let's use a real example so it's more concrete. Let's say you have a balloon. The balloon is filled with whatever, some gas, air. You blow up the balloon. And let's say you put that balloon in a room and you start taking the air away from the room. So you decrease the pressure of the room. Or let's say you take that balloon up to the top of a mountain. What happens to the balloon when the pressure is decreased? Close. Yeah, it gets bigger. It gets bigger. Okay.
Doesn't that happen with the cold and the heat or something like that?
That's with temperature. We're going to get to that one next. Yes. So if you decrease pressure, you increase the volume. Let's talk about why. The demo we're going to do on Wednesday, I guess we'll just kind of draw it and talk about it. We've got this bell jar thing, and we can put some balloons in there, and they're pretty small balloons with a little bit of air. Yes. Yes. Assuming the temperature stays the same. So we hook up a hose to this and we take the air out. We suck the air out with a vacuum. And then when we do that,
How is that possible? So,
what?
how is it possible to suck air out of
A space? Well, you can try right here. So this is hooked up to a pump in the building that is apparently broken. Okay. Going upstairs works. I hope our vacuum pump isn't totally broken. But anyway, there's a giant vacuum pump in the building, and at every station and at every hood, there's a little yellow nozzle that says vacuum. And when you open that up, the pump is turning and is taking air from here and just transporting it this way. And the power of that pump allows it to do that and hold that vacuum. So you're taking air out and leaving nothing in. Now, you can't ever get to a perfect vacuum. There's always going to be some air, but you're taking out as much as you can. It's the same thing like if you
put your finger at the end of the straw and dip it in a drink?
Right. Yeah.
It's enough. Okay.
Yeah, same idea. You're not creating a vacuum there. You're just not allowing the air to come in the other way. But let's say I'm not going to do this because I don't know what is in this, but let's say I put my mouth up to this and like sucked in. So I can suck some air out of here. Not a whole lot, but it gets like harder and harder and harder. So you can build a pump that can do that really well and get a lot of air out of it. So if we hook that up to the vacuum pump, the balloons get bigger, right? So we'll see this on kind of dramatically bigger. We'll see this on Wednesday. Same balloons. You haven't blown them up anymore. You've just changed the pressure and the balloons have gotten bigger. Another example of this happening is breathing. Does anybody have experience with breathing? All right, good. So that's another example of this relationship. What happens when you inhale? Now, I know what inhaling is, like everyone's going, yeah. Like what's happening in your body? Your diaphragm makes you have a lot, it expands your chest cavity, right? You expand inside of you. So you are increasing the volume inside your chest, which therefore decreases the pressure. So then how does that make you breathe? Yeah, if you decrease the pressure in your chest, now the outside pressure is greater than the inside pressure, and so the air rushes in from higher pressure to lower pressure. So when you breathe in, you're not really sucking in so much as you are creating an area of low pressure, and the air is rushing in to fill it. And then when you exhale, it's the opposite. You increase the pressure, which you can feel if you kind of close everything up and you go and you try to blow out, and I mean, don't do it too hard to like poop yourself or something, but you can feel some pressure building up in there. And then if you release or open your mouth or your nose, the air can rush out. And you create that pressure by decreasing the volume inside your body, inside your chest cavity. Okay, so that's this relationship. It goes back and forth. We wrote as an example, decrease pressure, increase volume, but it works the other way as well. Increase one, decrease the other, decrease one, increase the other, any way you want. The name of this is Boyle's law. And if you look at the book, you can see the equation, how it works mathematically and stuff. But again, we're not going to focus on that. Most important thing to remember is just that relationship. So pressure and volume are inversely related. When one goes up, the other goes down. When one goes down, the other goes up. And we'll see that on Wednesday. I think the book also has a picture of that here. You can see what's actually happening with the gas molecules. They have some numbers attached, but again, we're not going to focus on the numbers. So if you imagine a piston pushing down in a cylinder, you got the same number of gas molecules, but now they have less space to move around in, and so that ends up being a higher pressure. So they're hitting against the sides more because there's less space for them to move around it. So you decrease the volume by pushing the thing down, making it smaller, and that increases the pressure inside. Okay. Next one we're going to look at maybe volume and temperature. What happens if you get a balloon really cold? It shrinks. What happens if you get a balloon really hot? Okay, really hot, yeah. But if you get it like warm, it expands. Yeah. So how would you talk about that relationship in general? What are you doing to the volume or the temperature, or what are you doing to one? How does it affect the other?
As temperature decreases, volume decreases.
Yeah, as temperature decreases, volume decreases. And as temperature increases, volume increases. That's called a direct relationship. The name for it is Charles' law. Nope, not like that. There we go. And you can think of this in a couple of ways. The example we're going to do is kind of a fun one on Wednesday. We're going to have a pretty full balloon, and we're going to pour liquid nitrogen on it. Liquid nitrogen is at 77 K, so really cold, right? About minus 200 C. So you pour this really, really cold stuff on it, and it becomes like flat completely. Because you've cooled it down really, really far, and so the volume gets really, really small. And then when it warms back up, it comes right back to normal. No air has gone in or out of the balloon, but by changing the temperature, we can change the volume if we have something that can change its volume.
That's why if you breathe in really cold air, it like makes you have pain in the chest. Like,
No.
No relation whatsoever.
I don't know, actually. I don't know how bodies work. I imagine it has something to do with like, yeah, being really cold in your lungs. I don't think it has to do with properties of gases, though. Maybe.
Well, just because the whole thing with your pressure decreasing and increasing, what you were saying.
Yeah.
You think
I don't think that's what's causing like the discomfort, though. I think that's just the temperature against your cells in your lungs that makes it cold. I don't know. Ask a physiology teacher. Okay, so next, third of 4. Pressure and temperature. So the volume and temperature one, I guess if we're going back to that, that's also how air conditioning works, by the way. And what?
The autoclave.
Also the autoclave? Yeah, that's right, because you heat it to pressurize it. I guess that's the next one too, or like pressure cookers.
Yeah.
But with volume and temperature, with air conditioning, you have this compressed gas called Freon, or whatever the new Freon things are, and then it expands into a wider tube in your air conditioner. And that expansion, so going from small volume to a larger volume, causes a decrease in temperature. So we usually think about that second one as like what happens when we change the temperature, but we can also change temperature by changing the volume. And so we can cool stuff off through the expansion. That's actually kind of fits in number 3 too. In the real world, it's hard to isolate things in one of these categories because really they're all happening at the same time usually. But that's why we'll see some examples in lab where things are isolated. So what happens with pressure and temperature? Is that a direct relationship like volume and temperature, or is it an inverse relationship like pressure and volume?
As pressure increases, temperature increases.
Right. So what is that?
That's the inverse.
That's direct. Yeah. As one goes, the other one goes. That's called a direct relationship. So if we increase the pressure, we increase the temperature, and the opposite and everything too. Does that make sense if I just write it like that, or should I write it out in words? Okay. The way we're going to do that on Wednesday, we have this steel ball, steel sphere, with a gauge attached to it, a pressure gauge. Because what you need to do is you need to cool something without changing its volume. You can't use a balloon because balloons can change their volume. So we use a stainless steel ball that's fixed and can't move, can't change its volume. And then we put it in some cold water, some really cold stuff, and some hot stuff as well. We're going to change its temperature. And what we see is the pressure goes down. So we can't really see it because it's inside the steel container, but by cooling it down, the pressure goes down. This is something you might also experience in your car tires, like you think your tires are fine, but it's winter or something, and you go out and you turn the car on, and the little warning thing comes on, and you're like, what? I thought it was fine, I just checked it. But then you drive for a little bit, and then it goes off because it actually is fine, and that's because of this. because when the temperature goes way down, the pressure goes down. But then when the temperature goes back up from driving, the pressure goes back up. If that's happening, you should still inflate your tires because the tire pressure is supposed to be the cold tire pressure. Like what's the pressure when they're cold, not when they're warm. But that's why that's happening. That's why like you get to school and it seems fine and you think, oh, okay, maybe it wasn't a big deal. Because it is affected by the temperature. This one has a name also.
Do we memorize these names?
Yeah.
I was thinking about that. I don't know. I don't like memorizing the names. Like I don't think that's an important thing to know. It may be on the Blackboard objectives, but I would not put it on a quiz or exam. For me, the important thing is understanding the relationships, like what happens when you do one or the other. Okay, and then finally, this one seems really obvious, but I'll show you an example of how it sometimes isn't. The relationship between moles of gas and volume. Moles is like an amount, right? So if you increase the amount of gas, what happens to the volume? It increases. And if you decrease the moles of gas, you decrease the volume. But notice that it's moles of gas, not mass. And that's important because of the way that it can be affected by chemical reactions. So let me show you this example. Let's say you have a balloon filled with oxygen. Balloon filled with oxygen. And then you get all that oxygen in the balloon to react with itself and form another oxygen molecule called ozone. So that reaction looks like this. Ozone is O3. So if you do that reaction, is that balanced?
No.
Not balanced. How do we balance it?
So it looks like they're-
Yeah, we need a 3 over here and a 2 over here. Right? Okay, so has any gas left the balloon in the course of this reaction? No, it's all still in there. The mass of oxygen that's inside that balloon or the mass of whatever that's in that balloon is the same. Have the moles of gas changed? They have. Do you see that? They went from 3 moles to 2 moles. So they decreased by 1/3. So what happens to the volume of that balloon? It decreased. Even though nothing went in or out of that balloon, just in the course of the, got a little bit more extreme. Just in the course of the chemical reaction, the balloon got smaller.
What chemical reaction is that exactly?
It's one that happens, that can happen. It's not one we've seen before, I don't know. It happens in the atmosphere. It needs to be catalyzed by something, so it doesn't quite, it's not quite all of it there, but it's a good example for this, so I used it. I don't know, did you have some?
No, I was just wondering.
Just wondering, okay. Yeah, sorry, I don't have more information about it. We can look it up if you want. All right, so this one's called Avogadro's law. And again, this one's pretty clear when you're just talking about putting more gas in or out, but it gets a little bit interesting when you think about reactions happening inside of the balloon, and that actually changes the amount, the moles of gas, and that can change the volume. All right. So the way I would ask you questions about these kinds of things is something like this. Oops. So here's an example of a sample of initial gas. And we're going to think about what happens to that initial sample when we change these different variables. So which one represents a temperature increase at constant pressure? 1, 2, or 3? 3? Why 3? Yeah, because we know that when temperature increases, pressure also increases, and volume also increases. So 3 is an example of volume increasing because 3 is bigger than the initial one. And so that means if temperature decreases, what are we going to get? 1, because it's going to get smaller. What if the pressure increases at constant temperature? 2 is kind of the same, I think. So that would mean it doesn't change. What happens to the volume when the pressure outside increases? It would be 1. Yeah, the volume would get smaller. Because if the outside gets more pressure, it's kind of pushing that thing and making it smaller. And then if the atmospheric pressure decreases, you get 3. So that's the kind of things that we would want to, that you want to be able to answer. What happens if you do this? What happens if you do that? That kind of thing. Okay. So then the other part of this chapter that we need, okay, a couple things. So the other part of this chapter is how do we explain what's going on? Did you remember at the beginning of class we talked about the laws versus theories in science? What was the difference between a law and a theory?
Is it something that's experimentally proven? That's the law?
Not quite. They both need to be experimentally, they both need to have support of evidence.
A law has a conclusion.
They both can have conclusions. They actually speak to different things. A law is a set of observations, and a theory is the reasons behind those observations. So the law says, here's what happened, and the theory says, here's why it happened. It's not like one is bigger than the other, one is more important or more valid than the other. They both have to have evidence, they both have to be supported, they can both be disproven, all that kind of stuff. But one talks about what happens, one talks about why it happens. So we just went through a bunch of laws. Like let's take that first one, Boyle's law. Boyle's law says that pressure and volume are inversely related. You raise one, you lower the other. But it doesn't say anything about why. Why should volume decrease when you increase the pressure? It doesn't say anything about that. It just says it does. That's just the set of observations. It always does. So now we need a theory behind that that talks about why this is happening. And the theory the name of that theory is called the kinetic molecular theory of gases. So why all those things we just talked about happen. Now you can go in the book and read the specific sentences for what is all the parts of the theory. You don't have to really know that. I'm just going to give you the highlights, and then we're going to talk about how we use that to describe what's happening. So the main things to recognize are that gases are tiny particles moving randomly at high speeds. Okay? There's a couple other parts of this that that I'll tell you about, but we don't necessarily have to write down. You can read it again in the book. Gas molecules don't attract each other. So we talked about intermolecular forces in liquids and solids. Gases don't have intermolecular forces. That's not exactly true. They sort of do, but in some cases they do. But in most situations, we can assume they're not having any of these attractive forces. We also say that when they hit each other, it's elastic, which means they don't transfer energy to each other. They just bounce off each other and keep going. And all of that is, there's another thing that says they travel in straight lines. The really important thing of all this is the collisions with container walls is where pressure comes from. So when gas molecules hit the wall, that causes pressure. And we can use this idea to explain Boyle's law. So we say volume and pressure are inversely related. The way we explain that using this type of language is we say, when you decrease the volume, you increase the number of collisions with the walls. So if we're all running around in this room, and we have to run in straight lines, and when we hit each other, we just go the other way. If we're all running around in this room, and we have to run in straight lines, by the way, we're going to hit the walls, frequently, right? If we make the room smaller, but we still keep running the same speed, and there's still as many of us in here, we're going to hit the walls more, right? And so that's that increase in pressure. So that explains your increase in pressure by saying you're having more collisions with the walls.
What about a collision with each other?
Collisions with each other are what they call elastic, which means it doesn't do anything. You just hit each other and bounce off and go the other direction. So there's no energy transferred when you hit each other. But it's the collisions with the walls that cause this pressure. And then the other part is the kinetic energy of the particles is proportional to the Kelvin temperature. And what that means is that the higher the temperature, the more energy the gas particles have. And I don't know if anybody knows this from it's not that, from physics, but kinetic energy in physics is defined as 1/2 times the mass times the square of the velocity. You don't have to know that. But what it does tell us is that higher temperature particles are moving faster than lower temperature particles. The kinetic energy is proportional to the square of the velocity. So the higher the energy, the faster they're moving. The mass is in there also. So that means that at the same temperature, what's going to be going faster, a heavy particle or a light particle?
Heavy.
Lighter. Yeah, lighter one is going faster because the kinetic energy is the same. If the mass is higher, the velocity has to be lower to compensate. So at a given temperature, a heavy gas particle is going faster than a lighter gas particle, which has implications for things like pressure, right, of how fast it's moving. Okay, so that second part helps us explain the other rules. Like, let's think about temperature and pressure. Since temperature is proportional to the speed, if again we're all running around in straight lines in the room and running into stuff, if we suddenly start running a lot faster, what happens to how much we hit the wall?
More frequent.
We hit the wall more frequently, which means we increase the pressure. So that's how we explain the increase in pressure that's caused by an increase in temperature. If you increase in temperature, you make the gas particles move faster. And if they're moving faster, they're hitting the walls more. So that's where that comes from. So if you think about what's happening in terms of how it affects the collisions with the walls, you can explain all those 4 laws that we talked about in terms of what the gas particles are actually doing. So when I ask, like on a quiz, what causes the increase in pressure when you heat up a balloon, the answer isn't because pressure goes up when temperature goes up. That's just saying the same thing over again. The answer is, well, when you heat it up, you increase the speed of the molecules and that makes them collide with the walls more. Like that's a reason behind what's happening. So think about that when you're thinking about these things as like what's causing this and what's making this happen versus just, okay, this is the law and this is what it does. So think about what's happening behind that. All right. Any questions about that? The last thing that we're going to talk about with gases is partial pressures. And this has to do with what happens when gases are mixed together. So we'll say in a gas mixture, the total pressure is the sum of the pressures exerted by each gas. And that makes sense from what we just talked about. If we're running around and we're different kinds of gas, the collisions from one gas are some pressure, the collisions from the other gas are the other pressure, and the total collisions are the total pressure. So it makes sense that you should be able to add the pressures up together and get the total pressure. This is known as Dalton's law. And this is really important for like making gas mixtures or doing things with gas mixtures. Like if you're making a breathable mixture, you want a certain amount of oxygen versus other stuff. So you would mix those using the pressures. You'd say, okay, let's put in 5 atmospheres of oxygen and 10 atmospheres of nitrogen. I'm just making up numbers. Don't try to breathe this. I don't know if that's breathable, and whatever else you want to put in there, some kind of medicine or something. And you can mix those together based on how much pressure you put in for each one. And that would be an appropriate way to measure the amounts of each gas. There's a picture in the book that talks about this right here. I'll pull this for the notes. So if you imagine 2 gas cylinders or gas tanks, one with helium, one with argon. I think this is like a specialized deep sea diving type mixture with oxygen in it also. You could pressurize one cylinder to 2 atmospheres, pressurize the other cylinder to 4 atmospheres. If you put all that together in one cylinder, you'd have 6 atmospheres of pressure total. So you can use the individual pressures to get the overall amount. And this kind of just comes back to what we said at the very beginning, which is the way we measure gases is by their pressures. By saying, when we say this much gas, it doesn't mean it doesn't have mass. We could weigh it, but it's usually more convenient to use pressure to measure gases. Because it's just difficult to weigh them. If you think about something like helium, you can't weigh helium at all, right? Because it's lighter than air. So you can't put it on a scale because it will actually have negative weight. But there's still mass in there. So you have to use the pressure and the volume to figure that out. And we're not going to go through the equations to actually calculate all that stuff. So just kind of the general trends. The other thing you can do with partial pressures is analyze how much of each gas. So for example, in air, when you look at air in your body, this is kind of a neat table. You can kind of see what your body does to gas. So what this is showing is, let's say you have 1 atmosphere of air, 760 millimeters of mercury, and you inhale it. So that first column is what's the partial pressure of each gas of the air that's going in. You can see it's mostly nitrogen, then oxygen, with some carbon dioxide and water vapor. So then what's that air that's actually down in the bottom of your lungs, in your alveoli? And you'll see that the oxygen has decreased and the carbon dioxide has increased. And then what's the actual content of the air that leaves your body? You'll see once again that there's a little bit more oxygen and a little bit more carbon dioxide, and that's because of the diffusion into your cells and out of your cells. That carbon dioxide is important in your body for regulating pH, and of course oxygen for all the other stuff you need oxygen for. So you're seeing a little bit of that difference. And you can also see there's not a huge change. I think some people think that when you inhale oxygen, it's all converted to carbon dioxide, and then you exhale like pure carbon dioxide, and that's not really true at all. In fact, you're still mostly exhaling the same partial pressures as you inhaled. A little bit has been converted. And that's why it works to do like, you know, breathing for somebody or something like that, because you still have a lot of oxygen in your air. All right, questions about that stuff? Okay. The last thing I want to talk about is if this works, there we go, is not with gases actually, but it is something that's in the homework. Energy and chemical reactions. So we talked about exothermic versus endothermic reactions a few chapters ago. Remember that? Now we want to look at what that really means in terms of the changing energies of reactants and products. So the way we do that is we make a graph like this, where we put energy on the y-axis and the progress of the reaction on the x-axis. So going from the beginning to the end of the reaction. And since the energy is on the y-axis, we can plot our reactants and our products at various places depending on what their energies are. So in an exothermic reaction, our reactants might be at high energy, meaning less stable, and the products are at lower energy, more stable. So that from going from reactants to products, you decrease in energy. That's an example of an exothermic reaction. Because in decreasing in energy, you have to give that energy off to the surroundings. So you decrease in energy, energy goes out to the surroundings. The other part of the reaction dynamics here is that it's not a straight line from reactants to products. It kind of goes more like this. There's this extra hump. Does anybody know what that represents? Why does a reaction have to go up in energy before it can go down to form the products?
Heat.
Well, it needs some heat, yeah. And so this quantity here, like whatever this much is, that's called the activation energy, or the energy of activation. And that's the energy it takes to start the reaction. So how much energy is needed to get the thing going? And that's why a lot of reactions, like when we did some of those tests in lab, you had to go put your thing in a hot water bath for a couple minutes. That's what's going on there. That the reaction needs some energy to get started before it can get going. Same reason you light something on fire when you want to burn it. It would just sit there not burning until you give it that first energy to get it over that hump. So that's called the energy of activation. And then the difference in energy between the reactants and the products is called the heat of reaction, or the reaction energy. So how much energy is given off or taken in the course of a reaction. So then what does a endothermic reaction look like? What'd you say?
Starts at the bottom.
Yeah, it's the opposite. So it starts at the bottom, goes up like that. Because now the products are at higher energy. So you still have activation energy, usually a much greater activation energy in this case. But then also you're not recovering that heat. So that's a reaction that's getting cold to the touch because it's endothermic. But one thing we might want to do is decrease that activation energy. So if this is our reaction like we just had before, one thing we might do is try to find a way to decrease the reaction energy so that the reaction can proceed without so much energy being needed to be put in. And one thing that can do that is something called a catalyst. A catalyst is a compound that doesn't really, it's not like used up in the reaction, it's not part of the reaction, but it allows the reaction to proceed by a different mechanism that makes it go faster and that makes it have a lower activation energy. So like a lot of the processes in our bodies would never work on their own because the activation barriers are way too high. But when you add a catalyst, suddenly that becomes doable. Anybody know what the catalysts are called in our body? Enzymes, yeah. So that's what enzymes do. They reduce the activation energy of these processes by allowing them to go by a different mechanism. So to speed up a reaction, we got a couple things we could do. So first we could add a catalyst. That decreases the energy of activation and allows it to go faster. But maybe there isn't a catalyst for a given reaction. So the other thing you could do is, yeah, increase temperature. If you increase temperature, there's more energy available to help get over that hump. And then another thing you could do is increase the concentration of reactants. Or we could just say amounts. If you have more stuff in there, it goes faster. And that's because if we think about what's happening in a chemical reaction down at the atomic level, these different things have to actually physically contact each other. And in a lot of cases, they have to be oriented in just the right way. So like this side of this molecule has to line up just with the side of this molecule right at the right spot. If you increase the temperature, you make them go faster, so they're more likely to randomly hit each other just right. And if you increase the concentration of reactants, that's also going to do the same thing. If there's more there, they're more likely to contact each other at just the right spot. And so that works also. If we think about gases, something like increasing pressure can do that as well. By increasing the collisions between the reactants, you can cause them to go faster, cause the reaction to go faster, increase the rate. Any questions about that? All right, that went pretty quick. Let's take a look at a practice problem for that energy part, and then we'll call it a night. So we should be able to answer this kind of question. Is there like sports tonight that people are missing? I don't know. Isn't there like things going on?
Monday night football, yeah.
Football,
Might be a-
baseball? Okay, I don't know. Sorry if you're missing your sport. Okay, so a question like this. Here's a reaction. We've got sulfur dioxide and oxygen making sulfur trioxide. What happens to the rate of the reaction if we do each of these things? So if we add more SO2, what happens to the rate of the reaction? Speeds up, right? If we're adding more reactant, that's increasing the amount of reactant, so we're speeding up the reaction. What about increasing the temperature? Speeds it up, yep. We're making those gas molecules go faster, and that's gonna speed it up. Adding a catalyst, what happens there? Speeds up. Removing some oxygen? Slows down. What happens to the volume of the container after this reaction is completed? If it's done inside a balloon, let's say, what happens to the balloon? Why increase or why decrease? Do we wanna?
Because if the temperature increases from the motion.
Oh yeah, that's true. So let's say like ignoring all those other things, we just do the reaction. What happens to the volume if we don't increase temperature or pressure? The volume decreases. Why?
Because you're left with less moles.
Yeah, because the moles of gas have decreased. We have 3 total moles of gas on the left, 2 SO2 and 1 O2. 2 total moles of gas on the right. So just like with that oxygen to ozone reaction, we've decreased the number of moles of gas, so that means we're decreasing the volume. If you think about what that looks like on a molecular scale, so if SO2 is like this, it's not exactly like this, but that's okay. And there's O2, there's another SO2, it's more like that actually. Then when it becomes SO3, you've gone from 3 particles to 2 particles. And because gases are super far apart, and the size of the particles themselves doesn't really matter because they're so far apart from each other, that going from 3 particles to 2 particles changes the volume. Because now you have 2 things bouncing around colliding instead of 3 things bouncing around and colliding with the walls. So that's kind of why that's happening, because you're condensing it down into 2 molecules. All right. Other questions or things you want to go over again while we've got time? And do some go back to some equation type problems or. What?
But I still don't know how to name, but.
Naming?
I know it's easy.
We can try.
For some people, I just can't.
Let's do another big reaction problem here. I like to pull these out of the book because it's just let's just try this one reaction. And then let's say how much sulfur dichloride from 5.0 grams of sulfur. So you got to come up with a balanced equation and then solve for the quantities. So do you want to give it a try first, or should we go through it together? Give it a try? Yeah, give it a try first, and then we'll see. Also, don't be thrown off that it says molecular chlorine. That doesn't mean anything. It's just chlorine. I don't know why they say it's molecular chlorine. It's the same as if it just said chlorine.
Oh, always? Oh, okay.
I'm going to put down the reaction here and see if you got that, and then you can go on and work on this, solving the problems. So main thing to watch here is just that chlorine is Cl2. Just like hydrogen, nitrogen, oxygen, fluorine, bromine, iodine, always go as 2 when they're in their elemental state. So watch that because otherwise the equation doesn't balance properly. Do you want me to go on with the calculation or still working? No opinions? Go on? Or? Okay. So we start with 5 grams of sulfur. Set up our calculation from grams of sulfur to moles of sulfur. From moles of sulfur to moles of chlorine, which this step we can actually skip in this one because it's 1-to-1, but might as well write it out just because it's always the same. And then from moles of chlorine to grams of chlorine. All right, we can fill in these numbers from the equation in the middle. That's our mole ratio. Then our molar mass we can look up on the periodic table, 32 grams of sulfur per mole. Chlorine, 35.5 times 2 is like 71. If you want to be more precise, that's fine.
Wait, what did
Don't you do sulfur
Would
dichloride?
it be sulfur chloride?
Yeah, isn't it sulfur dichloride?
Oh, you're right. I'm sorry. Yeah, I was looking at chlorine instead. I got to read the question better. Sorry. Okay, so how much sulfur dichloride from 5 grams of sulfur? So we want to go sulfur to SCl2.
It's like 102, 103 grams.
102. Okay. 5 divided by 32 times 102. About 16.
I rounded and got 103.
Should be fine. Yeah. What'd you get for your final answer then?
16.09.
So close enough. This would really round to 16 because we're only using 2 significant figures anyway. But like we've always said, we're not gonna focus on the rounding issues. Okay, you want to do more? Or? Yes. No. Okay. Well, feel free to stick around if you want to do some stuff. Otherwise, I'll see you Wednesday.
You said the next time we're going to quiz, is that going to be on gases?
Not only, it'll be this and gases. So you get another chance at reaction type stuff too. Yeah.
Monday, after 6 and 8.
7.